Assalamu alaikum. In this video we will be covering topic known as sampling theory. So before moving to that sampling theory, first we have to understand the definition of statistical inference. Statistical inference comprises those methods concerned with the analysis of a subset of data leading to prediction or inference about the entire set of data. If I rephrase this definition, so I change it to statistical inference comprises those methods concerned with the analysis of a sample leading to prediction or inference about the population. The word subset of data is replaced by sample and the word entire set of data is replaced by population. So we have two things, one is sample and second is population. When we talk about sample and population, we have some information regarding these two things, sample and population. For instance, every population and sample has a size, a mean, standard deviation, a variance or differences of means. So population size is represented by a small capital N and sample size is represented by small n. Mean is represented by mu and sample mean is represented by x bar. Similarly, population standard deviation is represented by sigma and sample standard deviation is represented by s. Population variance is represented by sigma square and sample standard deviation is variance is represented by s square. Whereas if we talk about the differences of means, then population parameter will be mu1 minus mu2 and sample statistic mean will be x bar 1 minus x bar 2. Now what do you mean by these words, parameters and statistic? These information are describing a population or statistic. So population descriptives are known as parameters and sample descriptives are known as statistic. Now let's have an example of the sampling distribution of mean. Suppose we have a population data which is -2, 0, 2 and 4. So I calculated the mean of this data. So the value of mean comes 1, that mu equals to 1 and variance equals to 5. We are again doing an experiment which is to draw a sample of size 2 with replacement. When I started this experiment, so the first sample comes -2, -2, then we have -2, 0, then we have -2 and 2, then we have the fourth sample is -2 and 4, then the fifth one is 0, -2, 0, 0, 0, 2 and 0, 4. Then the ninth sample will be 2, -2, 2, 0, 2, 2 and 2, 4. Then the last set will be 4, -2, 4, 0, 4, 2 and 4, 4. putting all these values in the calculator. Let's have a look at it, that I am putting all these values in calculator. One by one, all values I'll enter in the calculator, scientific calculator, and then we will find out the mean and standard deviation of these data. As I entered this, I clicked on all clear AC, then we move to shift, then 1, then the fourth option is VAR, then the second option is X bar, and we have the mean is equals to 1. I wrote it here that mu of X bar equals to 1, the sample mean is equals to 1. Then I again clicked on shift and then 1, then again 4, and the third option then X sigma n, which is the standard deviation. I squared it for variance and I get the value of 2.5, that is 5 upon 2, if you can see that. I wrote it here, sigma X bar square equals to 2.5, that is 5 upon 2. So if I say that this 5 is representing population standard deviation and this 2 is representing small n, then we have the formula of sigma X bar, that is the standard deviation of sample, that is sigma upon root n. As you can see that mu equals to 1, the population mean is 1 and the sample mean is also 1, so I can say that mu X bar equals to 1, which is equals to mu, the population mean. When we talk about normal distribution, the random variable there was x, and the formula for z equals to x minus mu divided by sigma. But when we are talking about sampling, the random variable is changed to x bar and the formula for z changes to x bar minus mu x bar. As you can see that we are working on x bar, so I wrote here mu x bar divided by sigma x bar. Now x bar remains same and we saw that mu x bar equals to mu, so I write here mu, and sigma x bar equals to sigma upon root n, as I already showed you. So this is the formula for sampling, z equals to x bar minus mu divided by sigma upon root n. Now if we do this same experiment without replacement, as you can see that I am writing this without replacement, so the formula will be x bar minus mu divided by sigma upon root n multiply by under root capital N minus small n upon capital N minus 1. This capital N minus small n upon capital N minus 1 under root is known as finite population correction factor. This under root capital N minus small n upon capital N minus 1 is known as finite population correction factor, in short FPCF, which is approximately equals to 1. This under root capital N minus small n upon capital N minus 1 is always approximately equals to 1. So when I say that this capital N minus small n upon capital N minus 1 under root is approximately equals to 1, so the formula for without replacement changes to x bar minus mu divided by sigma upon root n. This formula is known as central limit theorem and is valid only when n is greater than or equal to 30. But if the sample size is not greater than or equal to 30, we will have the formula of t, that is t equals to x bar minus mu divided by s upon root n, and this formula is valid when n is less than 30 and the population is non-normal. Now the question is, do we have only one population for every time? So the answer is no. If we have two populations, then the formula of z will be changed by x1 bar minus x2 bar minus mu1 minus mu2 divided by under root sigma 1 square upon n1 plus sigma 2 square upon n2. And for t, we will have a formula t equals to x bar minus x1 bar minus x2 bar minus mu1 minus mu2 divided by under root s1 square upon n1 plus s2 square upon n2. Thank you very much. I hope you enjoyed the video and you understand this.